All right. Welcome, folks. This is our monthly Ask Mayfield Anything. I appreciate people joining in. I see some folks are still joining. So as we get going here, I want to welcome you to our data-driven lessons for safer CNI systems webinar this month. I have a couple great guests. So we're going to talk about just some of the findings that we've seen from this HelioVolta report and kind of some of the things that we're seeing in the field in general. So as we get going, always encourage folks want to hear questions from you. We did get a couple or questions when people registered, so we'll sprinkle those in as we get going. And if you have questions along the way, please use the Q&A function. There's, you can type your question into the chat there, and we'll see those and be able to get to those. So feel free to put those in at any time. We're not going to necessarily hold time at the very end for class or for questions. So sprinkle them in as we get going along. You see that we also have a poll here, so that information kind of just helps us in general. So appreciate you taking a second to fill that out and kind of tell us what you're looking for, and also help us for future webinars. So with that, let's go ahead and jump in a little bit. For those of you who may not know me, my name is Ryan Mayfield, founder and chief engineer at Mayfield Renewables. I've been in the industry since '99 now, so for a couple of years. And one of the things we'll talk about here, we're talking about just some implications and some code mandated changes in our industry. So we'll be definitely talking about that. But I sit on the code making panel, CMP 13. So that's one of my feathers in my cap that I really enjoy talking about. And so sitting on the code making panel, it's been an enjoyable experience. Looking forward to the next round, and hoping to make the code a better document, more usable, and for folks. But that's kind of the lens that I'm somewhat sitting in here with today. For those of you who are unfamiliar with Mayfield Renewables, we are a consulting engineering firm. We do both consulting and project engineering. Would love to talk with folks around solar and solar plus storage projects that you may have, and how we may be able to support you on those. And then also education and training is a big thing we do. Things like this Ask Mayfield Anything. We have a lot of online resources for classes. I'll get you some of that at the end of the webinar here as well. We do a lot of content that we put out there around something called Code Corner. We have a summit that we hold every year. So lots of opportunities to engage with us and do different education and training. So encourage you to take a look at that as well. All right. So a couple great guests we have today, James and David. James Nagel from CTO, co-founder of HelioVolta, and David Robinson, CEO of Sunup Solar Tech Services. Known both these guys for a while now. So James, I'll kind of turn it over to you first, just kind of go in order here and let you introduce yourself to the audience, kind of your history and kind of what you're doing, and HelioVolta and the report that you guys put out.
Yeah, thanks, Ryan. So hey, I'm James Nagel. Been very fortunate to have a long career in renewables as well. And I'm one of the co-founders here at HelioVolta. We're an engineering firm that provides independent technical services that ensure renewable energy assets perform safely and reliability today and for decades to come. We help owners and asset managers, off-takers, build comprehensive quality programs with robust EPC and O&M standards. And then we also provide root cause analyses of failure events, comprehensive field inspections, and data-driven benchmarking of partners and vendors. And I'll pass it to you, David.
Hi, hi. This is David Robinson, CEO, owner, founder of Sunup Solar Tech Services. As well, been in the industry since 2003. We primarily are a third-party pure play O&M services company. We specialize in QA/QC, commissioning, preventive and corrective maintenance, and some asset management for the CNI space. So we just basically take care of your systems, get them up and running, and maintain them for a long period of time. My experience and background has been in residential, utility, and CNI. So we're one of the oldest pure party CNI companies in the industry today. Just found that out, which is great. So it's really excited to be here. Mayfield and James and their knowledge and experience is great. And thing. So yeah, that's it. Try to keep it short.
Awesome. Well, I appreciate both you guys showing up. We've had a number of conversations, getting prepared for this, and so I'm excited to go through all of this with you guys. And yeah, the wealth of expertise that you bring is going to be great. So with that, let's kind of jump in. So data-driven lessons, safer C&I systems. So we'll get you some more information on this report that I've already mentioned. And so part of the deck that we're going to show is some of the data that got collected from the HelioVolta report. And one of the things that we're trying to accomplish here is just, having a broader conversation about, how can we make our systems safer? How can we do better, I guess, as a whole, as an industry, and trying to, you know, make sure that we are installing systems that are here for the long haul, that we don't cause unnecessary issues and things like that. I always like to start here, and I know David and James have their thoughts and everything on this as well. But when I start talking about code in general, I in my code classes I very often start here with the purpose of the NEC, and so you can see this language is actually straight out of the NEC, and so we are talking about practical safeguarding persons and property from hazards arising from the use of electricity. We're trying to make electricity safe. When we install a system, whatever that system is, an electrical system, we want it to be safe. We want people to be able to go up and touch it and be able to be around it without being, put in harm's way, potentially getting shocked or starting fires, things like that. And one of the things is towards the end of that language that you see on the screen here is, it's not a design specification. It's not an instruction manual. David, we were talking just a few minutes ago. It's not there to make your systems less expensive. It's there to provide a safe, functioning electrical system. And this is where we need to be a little bit forward thinking sometimes. Part of the conversations that we were all just having is, how how do we as code making panels, look forward and kind of project? And in a lot of ways, it's really hard in order to do that because industry's changing, we have technology changing, and then, how do we make these systems as safe as possible? So I don't know if you guys wanted to add anything to that in terms of, where you sit and kind of, especially around code and how it fits into your day-to-day world, and how you use it.
Are we talking about behind the fence?
No, this is all C. So we're just basically talking all C and I. So this is
Yeah,
all, this
yeah,
is,
yeah.
yeah.
Yeah. I think Brian, you said I mentioned that like when we're in the O&M space, or like after we get a system, it's built, Spectre goes away. A lot of our challenges is working around manufacturers. So and manufacturers, they're building stuff on their specs, and code, it does not apply to them most of the time. It's out of the box applies. So a lot of times we're in the components, we're in the hardware, and identifying why is it failing, what went wrong, how did it get installed this way, and we have to solve that problem immediately, right? We don't have weeks or months to figure it out. We go out there, we're on site, we have to implement a solution. So what we've been able to do is really identify, training, partner with manufacturers first, identify engineers that work there that we can get on the phone with and be on site, share information, and then find the proper test equipment we use to identify certain solution problems in the field and figure out how to do that, and then train our guys consistently on a daily and weekly basis on approaching challenges. So yeah, so code is a suggestion in a lot of ways in the O&M space, because we're dealing with a lot of manufacturers and how they installed it.
Yeah, thanks. And I would just add, you hit it on the head there too. Like instruction manual is not what we're looking at, right? If you build just to the code, like you're not going to get an A+ on your quality. But it kind of comes back to that focus around like safeguarding persons and property. And a lot of our focus is often on like really safeguarding and protecting first responders as they're coming onto a site. They might not have the depths of training like specific to PV and like power systems. And so like having that mindset of protection and safeguarding people is a really thing I would just want to underscore with code. And right, that's if that's the intention, are we meeting that intention as well?
Yep, and one of my favorite things of saying is if you install the code and we are grading people, you get the C minus, you pass, but there's always best practices. There's always things that we can be doing a little bit better. So, but the fundamentals here when we're installing systems are trying to make them safe electrical systems for people. I want to move into kind of a little bit of history so much, but talking about kind of this expansion framework of code, kind of what how code can evolve and what we have seen in the past. And around this, so you see that we have kind of just four big bullets here. Not we're just talking about some items that were not in code originally, got added into code. And so one of the reasons I wanted to put this in here was we have seen safety features added into our PV systems. And so these bullets are very focused on PV systems specifically and things like ground fault protection and arc fault protection. Those are safety items that on the AC side, we're probably quite familiar with. We've seen for a long, long time. And in our homes, our businesses, we have ground fault protection, we have arc fault protection. And so there was this inclusion of those in for our PV systems. And one of the things I like to point out is when we added those, we didn't have listed components. We didn't have listed ground fault protection, DC ground fault protection units that we could just go buy off the shelf and install. So industry was reacting to code, and I would say, for those specifically in a very positive way, we have systems that are, there are ground fault issues, there are arc fault issues, and so adding those in was important, and it was something that we saw as an industry, and then kind of adapted to it, if you will. I put in connectors and hazard control systems or rapid shutdown there as well. Those are things that are also evolving. We've had connectors. We've had that bottom picture. If you can pick it out really well, there's the old MC3s on those. So for those of you that have been in industry for a while, when the connectors first came out, they were the MC3s. They weren't locking. They weren't truly locking. They didn't have the tabs on the side where you clicked them together and you could hear them snap together. They had some friction. They had some ribs in there, and you push them together, and you had to pull them apart to get them apart. But there was no locking mechanism there. So code put in some provisions around needing locking and latching for those connectors. And so again, industry having to respond to that. And then rapid shutdown, as I'm sure as we know, and we're going to talk a fair amount about here today. Another thing that was added to the code in the effort of making systems safer, reducing shock hazard, especially around firefighter interaction. And that was, the intention around those, as I would say. Um, I'll open it up, David and James, how you've seen that the expansion framework of code on that.
Yeah, thanks. And I think, we've talked about this before. Code is going to evolve. It makes sense. And that's just the nature of it. And you said before, like code is trying to look into the future and affect change in a safe way. And I think like particularly with ground fault and arc fault, we really had a better sense of what that takes. It's not a unique thing to PV systems for ground fault and arc fault detection. But really understanding the need for connector, like diligence around connectors and like rapid shutdown, the foundation of that is just really different. And so we may have pushed the code in a direction with really good intentions, but the foundation for that push, you know, is didn't have the same foundation as ground fault protection. And so we're kind of understanding, did this help or hurt, from a reliability perspective? And you kind of mentioned with the connectors there, right? We were able to have that correction to locking tabs and this type of thing to make things more safe. And so we're kind of understanding the path that we're on and if there needs to be a redirection. And I think that's just the nature of code.
Great. David?
Yeah, no, I mean, I guess speak more to about like what happens in the field and the reality of the situation most of the time because I've seen it. We went from our ground fault protection was just CTs, then you had inline fuses, and then now you've gone to then you had arc fault detection. And every time we're introducing those things, we're introducing a different way on how to capture those things, how to troubleshoot, how to identify it, because you're adding layers to systems when they fail because they do fail. How do we go about troubleshooting them and accounting for them and finding failures? So our equipment on how we test systems has changed a lot from when in 2006 and five when we were troubleshooting systems to now where we have equipment that we're looking for series resistance in the strings that can pick up and identify and start modeling and predict arc faults before they happen. So we're kind of at that stage with that. And then you introduce the rapid shutdown devices. The biggest problem with them is that before you had your panels connected in series and you could test at your points of your positive and negative home runs in your combiner boxes, right? And then you can isolate that. But now you have to have extra equipment, and it slows down and introduce a lot more cost and time from an O&M standpoint. And also you're introducing way more connectors and way more failure points. So it's, from my perspective, is more of like seeing it historically how I'm always reacting to code. Like I'm not in these rooms, having conversations of like how this is going to affect how we maintain, commission, and test these systems to validate that they're going to operate they're supposed to. And then in addition to that, when you have changes like that, training and education from top to bottom. Like how many times when I was in charge of commissioning a huge portfolio, I'd look at the plan sets and the engineers it was just wrong, or the EPC didn't read the manufacturer on how it's supposed to be installed. So taking the time to understand how to implement these new products that are getting onboarded, I'd say, based off of code is another huge factor, which is why, training is a big conversation these days. But, we as an industry, a lot of our training is on the job, and especially in C&I, which is specifically unique to the industry because you're dealing with huge voltage and current potentials like you have in utility, but you deal with the scale like you have in residential. So that diverse and complex situations on each site is unique. So, but that's why I like it. That's why I love. It's so much fun. So, yeah, every day we see it. So I guess that's where I should stop talking.
No, yeah, no, I think you kind of no. I'm not asking you to stop talking. So actually, you kind of led into some of this, and so we'll keep the conversation going. Actually, around so we those last things, the last slide, we talked about some of the additions, the safety additions to code, and in the prep call, we were actually talking about how much more difficult it is on the DC side to like arc faults, for example. Be measuring those, be finding those, and be able to effectively um, yes, this is an arc fault and we should be shutting down. I think, I mean, David, you probably felt it as much as anybody else in the field when arc fault was introduced into the code, and going in and having to go track down. Was it really an arc fault, or is it a false positive? Because it's noise, it's electrical noise in the line, and
Yeah.
how do we measure that? And so all of these things, I'm saying these things because there are challenges all around. It's not just any one part of the system. It's not any one component or one thing. Everything has their own set of challenges. And quite honestly, it's been interesting to me to see where that falls, who that falls onto in terms of responsibility when it comes down to it. So I'll just stick with arc fault for a second. It just landed in the lap of inverter manufacturers. That was the piece of electronics that's being installed at that time when that was introduced. And made kind of the most sense to have it there, but at the same time, it's like kind of not, I hate to say fair, but it wasn't kind of fair to the inverter manufacturers to have to take that on. But that's where it landed.
Yeah. I mean, I have personal experience where we work with manufacturers and we had to deploy that and we were installing hardware, after, we're coming in and we open these inverters, we install this piece of hardware, we plug into it and we watch the signal. So we were learning about how the arc faults and how they were actually capturing and detecting it. And, the interesting thing is depending on the module, like the manufacturer and how they would bond to ground would change the signal. and would interpret like would cause false arc faults, or you'd have loose connections, which is actually is a good thing. Arc faults, I think, from a code standpoint is good because it does it does create safety and reduce risk in systems failing. And it does it very well, but you have to understand and work with manufacturers and figure out how they're actually capturing that signal, because that's a huge important that we're running in today. Like these older systems that have was it PID? Is that the correct phrase for it? PID, and then that might be causing false arc faults now. And so how do you detect that and pick that up?
Mm.
Or now we're picking up. Now we're in situations where we have equipment or where we can run a series resistance. We find that it's a connector or a module or RSD. We fix it. But if that inverter manufacturer has a different calibrated scale of the arc fault, it still may trip it. So this is a whole, which is fun. So, um, but then
Yeah.
again, if I'm a developer or an engineer, you're looking at costs, right? And then the whole O&M side of it is very different, because you're trying to like predict costs in the future when you design and install these systems. And so you have a significant increase because you're creating these false failures, but also you're losing production at the same time and incurring costs and truck rolls. So like every time we add another layer of code, how does that affect increase the kilowatt hours, like uptime of the system?
System
And then
production, sure.
yeah, and then that cost of labor is continuing to rise. So you're predicting it at in 5 years, your labor is going to be way more expensive than it is today to do a truck roll. So this is like everything that constantly happens. That's why I love code. It's a great O&M generator.
So James, I guess you maybe have some stuff to say on all that, and I guess I would love to. You guys are out doing inspections, doing QA QC work. Can you speak to kind of the change in installation methods, and one of the things that I think we're all seeing is this emphasis on speed, making sure we're trying to get these systems installed faster onto the next job, and kind of what that impact is.
Yeah, and I think we really see this like based on like vintage of the system. Like what was the COD of this system? And you can really see a trend there. And we really saw that, probably around 2014, 2015, 16, we started to see that real uptick in the maturity of our industry as well, where you just saw so many more installations getting put in. And so, right, to meet that demand, you had to move a lot faster. You had to, like, the labor costs were increasing, and at the same time, like, you needed to move faster. So, we and David, you kind of mentioned this a few days ago, where we had such a craftsmanship approach to a lot of these systems. Um, in the more nascent years of the industry, but as we matured, we really dialed in the financials of it and needed to make things more cost competitive. And so, right, things will get installed, per code and all this stuff. And you might have latent failures in those systems, right? That might not pop up until 5 years later. And right, your EPC warranty might be expired by that time. And who really has to deal with that issue of failing pieces there. And so that's just something that we've seen a lot of just over time. As the industry has matured, there's kind of that balancing act where we need to move faster. We need to, do more systems in a day, right? And we're also introducing new components based on code that may not have the long background of testing that we would expect. And so there's just kind of this flow of almost failure every few years that then informs the next batch of systems, um, system designs. And so I think one of the biggest risks that I see there is when we work with large portfolio managers. Um, they don't have the appetite for failure, right? They might not be in the business of, this is particularly for CNI, right? Their core functionality, their core like business model is not having solar on their roof, right? And so if solar on their roof is jeopardizing their core business, well, then they want to scrape solar off their roof, right? And that gets media attention, right? And so that's one of our really big like existential concerns, I think, as an industry, that as we move really quickly, there's some really big risks of these failures. Um, where, if large companies scrapes off all the and just kills their solar program, then other big teams will follow suit. And then, your CNI division of the market really gets hammered. So that's just something that we've seen just kind of in the industry trends there.
Yeah, and I think it's an important thing to kind of be aware of and be thinking of is yeah, what those implications are. And the big players who's when we have whole portfolios of nationwide systems, people changing their methods, it's important to pay attention and as an industry and be looking at that. I do see a good question from John Inslee. Kind of, we're going to move away from the arc fault, so I want to throw this question in right now, or the kind of the comment. He was asking about arc if there's circumstances where the rapid shutdown signal from say a transmitter could cause an arc fault signal or cause an arc fault within the at least the signal or the noise making it seem like there's an arc fault. And I know that there's a lot of there can be issues, I guess should say, about using different components. And so this is where I'm going to have a slide here in a few minutes about working with manufacturers, getting trained and things like that, and making sure that the components are known to work together. So we definitely have seen situations where components get put in to meet code requirements, but they don't talk to the inverters, or there are these issues, these communication issues. So can't point to exact situations, and I'll throw that over to David and James if you guys have seen any, but situations where, yeah, that is possible for a signal, a rapid shutdown signal to cause some noise in a line that might be conceived as or construed as an arc fault.
I mean, the issues we typically see with crosstalk is probably what he's referring to, or something like that. You're telling the rapid shutdown, and we're specifically you guys talking about rapid shutdown devices, not MLPEs. So in regards to rapid shutdown devices, that signal gets crosstalk, and what happens is it's causing the device to open and close rapidly, and
Right.
that's what typically will cause the arc fault.
Right.
I don't see the signal itself causing like a false arc fault. We haven't had the opportunity to dive and diagnose it at that level. But the most common problem we see with rapid shutdown devices is just crosstalk, and that goes back to installation and design, right?
Yep.
Specking out, having really good detailed plan set. So that's
Yeah.
I see that.
And actually, that's the exact example I have on one of the slides coming up is around crosstalk. So we'll definitely talk about that. All right. Let's jump into the data. And James, I'm gonna kind of turn it over to you and have you lead us through this. And definitely, David and I both read through this report, and hopefully a lot of the folks on the call as well. And kind of what is it that we're seeing? Kind of how you set the report up that you just released, and kind of what the key findings were.
Yeah, thanks. Um, yeah, and so this is available on our website. I think we'll put a link to download this in the chat too. But basically, just setting this up. So HelioVolta, we use SolarGrade as a fieldwork management software for everything we do. And so over many, many, many projects, we have a very structured data set on the work that we do, and that really accurate or like well documents well the asset health of a system. And so our data set is primarily focused on CNI and utility. So I just want to caveat that like residential is not something that we touch very often. And so with such a structured data set, we can really carve out that data to have a more meaningful conversation. So if you just are, noticing trends in that data, then you can kind of double click on it in a lot of ways. And so we're seeing a lot of incidents, safety incidents pop up concerning RSDs, right? And so, let's look at our data set, let's trim out all the utility scale and just look at CNI, right? Because we don't need RSDs in utility. And so with that, we have a lot of these findings on, with systems that do have MLPE and RSDs and systems that don't, and, kind of comparing those two. And it might be helpful just to do like a really quick caveat on when we talk about MLPE versus RSDs. RSDs are really a subset of MLPE. We kind of categorize MLPE inclusive of RSDs, which are just the pure play code compliant, like I can meet the RSD, the rapid shutdown code requirements. That's kind of when we say RSDs, that's really what we're focusing on. We also have microinverters and optimizers under that category of MLPE as well. And so, I want to say that like everything fails, sure, but this particularly focuses on rapid shutdown devices, RSDs, as those we know fail significantly more often than other systems or other device frameworks. And so with that, we really try to double click on that and look at, you know, systems that didn't have RSDs and systems that did, and compare those two. And that's kind of the foundation of the report that we put together. And the idea here is kind of what I alluded to earlier around, as the code evolves, we just have that evolution can be a little bit more fruitful when we have data-driven conversations behind it. And so that's one of the big intentions here, because nobody wants this, right? Nobody wants to have these reliability issues on these project sites, and so that's a big part of this. So one of the, and maybe we can go to the next slide. I think
Yep.
helps. Yeah, hopefully.
Yep.
Oh yeah, there it is. When we, at the end of the day, if it's a installation issue, if it's X, Y, and Z, if like the exact cause is very important, but it's not, at the end of the day, if we're having more reliability issues in the systems, that's kind of a little bit more meaningful, right? At the end of the day, are people more safe? Are we having fewer fires? That's one of the things that we really focus on here, particularly with like firefighter safety, right? If you have more fire truck rolls out to a project site than you had before RSDs were implemented, you know, we haven't met the goal of the NEC in a lot of ways. So how do we inform um, the code so that we don't put our first responders and people in general in harm's way more frequently? We're going to have a lower frequency in that. And so what we saw here is just like really comparing projects with and without MLPE, right? Beyond just the RSD prone failures, when we just look at the topology of the systems themselves, when you introduce more complexity in a system, right, you just also create more failure points. And so, this is one of the charts in the white paper, go check it out, right? Where, if we just focus again, right, data set, just focus on connector issues and segment my data in those different ways, right? I have that many more issues when I introduce MLPE, and that's just connectors. That's beyond the device failures itself. If we go to the
And
next,
so
oh, go ahead.
I was just gonna ask on this just a little bit of a on some of the sub bullets there on the bottom. So things like
Mhm.
that, I see a big jump in the intermated connector. And so is that you're in that situation, you're talking about module to device and that connection
Mhm.
specifically, as opposed to if that And to me, that jumps out as like one of the biggest, or maybe the biggest jump in the issues. And so, is that what you're talking about there? The connection from the module to the device itself?
Yeah, good question. That's one of the connectors, right? So intermated is if I have an Amphenol to an MC4 or something like this.
Okay. Oh, okay.
That's an intermated connector. And right, the real core issue there is like the plastics, and we were talking about the locking tabs earlier. The plastics might connect seemingly well, right? Then it's not
Hmm.
like a listed device together. Like it's not tested together. So what
Right.
really matters is the metal inside those connections. And if those pins aren't specifically designed to mate with each other, then you have a high resistance connection there, which can lead to thermal overheating. And
Quick question, James, about the data in
yeah,
relationship to the connectors. Are you able to separate field made connectors and factory connectors in relationship to the failure points?
we do. Yeah.
Okay. So is that like, so all this data that we're, it's relationship to connectors, that's all field made, or is that a combination of both?
It's in this instance, it's a combination of both.
Okay.
Yeah. Mhm.
I'm
Yeah.
just saying that because
Good
most
question.
of the failures we see typically are related to field made
For
connectors.
sure.
Yeah.
Yeah, for sure. Yeah, and I mean like factory made connectors, and we usually include like warehouse made connectors in that case. If it's not made on site, right? Because you really have to dial in your process for on site connector making, because there's just so much more variability you can introduce there, right? Tooling, is it torqued correctly? You know, if I have debris in the connector as I'm making it, right? If it's like left to sit out there. Um, yeah, I could probably talk for like few,
Yeah. No, I just curious.
but yeah, that was a good question.
And there was a question that came in too, and I think that reading it right. So the what we're looking at in the graph here, so it's
Mhm.
issues per megawatt versus with and without MLPE. And so is that saying that we have, upwards of, one and a third to up to almost two issues per megawatt? Is that how we're reading that?
Yeah,
Just on the connectors specifically.
on this one specifically, yeah, it was really helpful to normalize, on a certain way, right? Like where if I have a 7 megawatt rooftop and a 500 kilowatt rooftop, one's going to dominate. But if I like really, in terms of the data, but if I normalize on a per megawatt DC basis, I can get a little bit more of a quality score out of that.
Okay,
And
cool. And
one more question is, are you, when it says MLPE, is this just a typo? Is this really RSTs, or are you actually including, you know, panel level inverters and optimizers as well?
Yeah, good question. So this is inclusive of the various MLPE um, uh, topologies. But in this case, this specific graph, and the next one too, actually, is dialed into not the device themselves, but right, the implications of those devices, like the connectors that are connected to those devices, right? So if I if my module to RSD uh, connection, right, is intermated, I might have to introduce a jumper so that I avoid intermating. And so that uh, the term is combinatorial explosion. There, where if I have that many more failure points with connectors, that's really what we're trying to focus on here. As you introduce more and more complexity in a system, um, you just introduce that many more failure points.
I'm just going to bring up one point. Jeffrey actually made the same point in the questions. And well, one, so the intermated, I'm glad I asked that question to get to a little clarity. So the intermated it was addressed in code. So there is a code reference that says that you can't do that. Basically, you have to have them listed and identified for being intermatable, which I think to everybody's knowledge that doesn't exist, at least not today. So Amphenol and Soybean, they don't have connectors that are intermatable. Unfortunately, that yes, that is in the code, but One, how often is that, inspected at that level for large scale farms? That's one. Two, we were marketed as an industry of, compatible connectors. So we were told these are compatible together. And so before that was even a code thing, we were doing this. So a lot of these are probably legacy systems. So, Jeffrey, 100% agree with you. It is a code violation, but it's also, that how long ago were we doing this before it was a code in a code thing, and then also just kind of the way it was. um, we were told as an industry these are, and they look the same, they click together, you hear it, it sure sounds like they're it sounds like everything's okay, so I'm just going to move on. So I think it was another kind of broader issue within the industry.
And I'll say that like we still see new projects with intermated connectors. So I think it kind of comes back to that idea of code is pushing in this direction, but it's sometimes it's hard to keep up with that to like really stay knowledgeable around that. And kind of right coming back to uh, one of your core values as a company, Ryan, right? Like training is making sure that we're all on the same page with that stuff. Because we still see it, and right, it comes back to like the inspector didn't like fully appreciate that you can't have intermated
Right.
connectors.
Right. Well, and even, it takes somewhat of a sharp eye, even I would say, within, because a lot of times they look very similar,
Yeah.
and unless you're like digging in there, you don't catch it. I'm keeping an eye on time. I know we have a lot more to cover. We could have done this in 2 hours. David, I did want to. There was a question that came up before, and we talked about it in one of our early sessions on, and it'll kind of be my last connector thing, and then we'll move on. But the question was around field checking in those connectors and being able to do that without doing destructive testing. And it felt like you had a comment on that and just kind of what you guys are doing around checking connectors. And you had asked the question around field made versus uh, factory made connectors. And so I'm curious on, how you guys are handling that to when you see field made connectors.
Yeah, we're doing series resistance testing, which is with a new tool, which is not common right now. It's not
Hmm.
insulation resistance testing. It's not VOC. We're not using IV curve tracer. It's just a series resistance testing, which is mimics arc fault detection, what the inverters are doing. So we just have a device that plugs into it, and it's been very. I've been able to identify tons of arc faults, and then now we're in the mode of where we're creating it as we're building a model out so we can start predicting it. So as we go do PMs, we're implementing this new test and creating trends to see that series resistance and note where it's failing. So it's been really a game changer for us as far as being able to, you know, train our guys. The tool's fantastic because it's safe to use. It really is educating our technicians because that's our big core here at Sunup, and part of partnering with Amicus O&M. We're one of we're part of them as well, and I'm on the board to help develop training for field technicians. We really focus on field technicians first and giving them all the fancy tools, right? So in addition to that, you could do thermal imaging, right? We have trained our technicians, or
Hmm.
you have thermal imaging, but this one allows us to also test through RSDs and pinpoint RSDs as well. So
Okay.
we have methods where we can test the string and it quickly identifies. We can go through that string and break it down and identify, is it RSD, is it the module, or is it a connector, through series
Perfect.
resistance testing.
Perfect. And that's Amazis, I believe, is the tool you've been referring to.
Yeah,
So,
yeah.
so I'm making a note mentally about needing to talk about that field testing and that kind of stuff. So, future classes. So, with that, I'm going to keep us moving on. We're running low on time, I know, because we all have a lot more to say here. But so kind of moving through on the report a little bit, James, talk about wire management, MLPE installation. So kind of, I guess, walk us through this one a little bit too.
Yeah, and so I think, the previous one was on connectors, this one's specifically wire management. And I think one thing to underscore here is on these charts, it's specifically more major and critical issues, right? Those are resulting in like actual safety and reliability issues, right? Um, do I need to shut down the system? Do I need to get somebody out there ASAP? Am I putting people and property at risk. And so that's a big piece here. And we see that, in connectors implications in the previous chart and in this one, really like wire management. Again, that complexity increase has a lot of reliability issues. And they're not just like, oh, it doesn't look good, or there's a wire resting on a roof. It's meaningful deviations from safety expectations.
Great. Yeah, and I think that, all of this is all helpful data to look at. And as I'm looking at this chart, and one of the things I wanted to, look at, and we're going to talk about this next, but crosstalk shows up there on that. So for those who are maybe not familiar, crosstalk is when we have module level devices are using power line communication to do that communication, makes things more simplistic in terms of the installation. If you can use the same wire that you're running the power, that the voltage and current on, if you can use that same wire to communicate with those devices, seemingly makes that a lot easier. But the crosstalk is there's a signal that gets sent out there from the transmitter, and so there's a very specific signal. And if you have multiple signals in close proximity to each other, they'll start to mess with each other. It's kind of like the way it was described to me was you're driving. For those that remember listening to the radio when you were driving from down the road, and you start to transfer from one radio station to the other, and it's just you start to get this jumbled sound from two different radio stations on the same frequency. That's kind of what happens, and so you can't decipher, are you listening to the country station or you listen to the rock and roll station anymore, and they start to get this crosstalk, and they conflict with each other. So just a 30-second, hopefully, um, thing on crosstalk there, which is a huge issue we've talked about before. We've done a lot of um, uh, information that we put out there on that, and this being actually one of them. So I'm going to, again, just kind of keep us going a little bit. We have the next slide is a good one too. But one of the things we've talked about this, I think we've all said this now, education and training being a big thing. And so one of the things I want to kind of bring to light is, or not bring to light necessarily, but to make sure that we do talk about is, the manufacturers do have their instructions. There are manufacturers that do a lot of work in terms of trying to train people and get that information out there, the proper way of installing the equipment. And I think it's kind of easy to point fingers and say this is, the fault of this device. And it's also quite easy to point fingers and say, well, you didn't install it right. And so I think it's a combination of everything. We need to make sure that we're using products that are, proper for the installation, and we're installing them properly. So I just wanted to throw this out there, put this slide in here. It's talking about, we do have manufacturers, we do have installation instructions, that we do have manufacturers going out and trying to train people, and not every component is going to get installed the same. So we actually have some confusion amongst the industry of, do I install it in a specific one order for one manufacturer, to the module first and then to each other. Different manufacturer may say no, install them together and do the series wiring for the devices first and then to the module. So understanding that's going to play a big role in, do these devices work or do we cause problems? And so I hate to harp on the drum too much, but read the free manual, as Greg Smith would say. That's definitely something that we want to encourage people to do. Make sure you're installing it right. And this gets into, I'll kind of get off my soapbox here a little bit. And David and James, you're welcome to jump in here, but kind of what those installation practices are, the education and training. David, you mentioned Amicus, and so there's organizations out there trying to help us do better.
Yeah, I mean, it's best to work with the manufacturer directly and go from there. And the big thing you want to ask yourself, do you have the latest version of it? Because you have different versions that change, and so you got to make sure you have the latest one, because historically, because of my time, I've seen a new product comes on after it's been in the industry for 5 years, they figure out the kinks, and now it's like, this is how you really are supposed to install it. So
Right.
and engineers, so that's a lot of question for, like, you got to make sure and to work with the teams in the field, the EPCs, the engineers, ask those questions. And our approach is always, we're always learning. Solar is complex. It's fun. There's so much information out there, and we're always growing and learning. So the big takeaway from that is reach out to the manufacturer, read the manual, but also ask the question: do I have the latest and greatest, um, you know, manual notes, and go from there. And then have those conversations with the engineers and reach out to them. Sometimes they miss it and they're like, oh, that's a great point, and can work with the EPC teams to install it correctly. And then having a third party QA/QC team as well that has a lot of field experience and vision that can also be a check for EPC and engineers, and work with them in the light of not I gotcha, but hey, how can we all learn together? Because every single group brings something unique to the table, and as long as you have that culture and that share, that transparency that you're speaking about, James, with data, I think that's the best way we've seen to have systems that are successful.
Yeah, 100%. And definitely like that's something that we name a lot of times of, in conflict resolution, hopefully, sometimes it escalates to that. But at the end of the day, one of the frameworks with conflict resolution is interests and positions. And, we might have different positions approaching a system, but our interests are generally the same around reliability and quality, right? Nobody wants to install an unreliable thing. So it's helpful to like start from those interests and align on that collaborative nature of, okay, we're QA/QC, on site. We're not here for the gotchas, right? We're here because we all collectively want a more reliable system, more reliable portfolio, more reliable industry. Because then it's just safer overall and grows more successfully.
Yeah,
I love it.
it's fun.
Perfect. Okay, I'm going to move us into this probably is our last slide here of our content, at least, and so we can spend a few minutes here. But yeah, this is more from the report, and so both David and James, you have the field experience. You've both seen these kind of failures in various forms. These pictures are somewhat unfortunately eye-catching, and some maybe a little bit more than others, but some of these connector ish or excuse me the field issues, and so connector mismatch is one of those. Is the first thing that we have on there. But yeah, I guess this is born out of the report, James. And how are you? Were these the top ones? Is this kind of the top down list of in terms of that was some of the questions? I was scrolling through the questions. I think this will answer some of the people's questions around where are we seeing the most failures, and what are some of the best ways to avoid them?
Yeah, so it's definitely, I mean, I think we've covered a lot of this already, where just installation means and methods, just aligning with installation manuals, that stuff. And some of that is, positioning in the module, right? Where if I tuck it under the frame, I might not get the airflow that I need for like the natural cooling of that device. So like things like that, maybe in the latest version of the installation manual, but maybe you don't catch that. So like pieces like that can have a meaningful effect. We also see people kind of compensating for distrust, right? So like positioning them in the module, but also positioning the rest of your system, where some people are actually adjusting ballast so that they're right underneath the RSDs, so that if they fail, you have a non-conductive surface that's more thermally resistant as well, to avoid wider
Interesting.
spread failure. Yeah, it's wild. And then, I mean, like other O&M best practices, we push a lot towards UL 3741. You'll see that in the paper as well. But kind of that MLPE versus non-MLPE, hindsight is always 2020, right? Like, oh, if we hadn't installed this, would be in um, this situation. And one of our industry partners, they have a fleet of projects, right? And they installed RSDs in one of them, didn't like it, and in their entire rest of their fleet, they don't have them, right? And their happy about that decision, right? They haven't seen the reliability issues that are underscored by a lot of the data that we've seen here. So there's some meaningful backing to the avoidance of that
Mhm.
increased complexity and risk there. Um, yeah.
I was just going to bring up. I see a question here from Rob, and it kind of gets into the connector mismatch. And it's a good question. I think it's one that gets asked a lot. Is the question is, if you have a module that, or you're looking at components, maybe it's a module says it's MC4 compatible. Um, what are people to do here? What's the answer in terms of you have a connector A, connector B? I'll stop using brand names just so we're not throwing anybody under the bus unintentionally. You have connector A, connector B. Nothing's, they're not intermatable. They're not listed together. So how do we make that connection? And I think what I've heard from a lot of people is, well, you make a jumper that goes between the two. You get connector A's, you get the right one on that side of the wire, you get the connector B on that right side. And so, of course, now all of a sudden we've just doubled more the number of connectors we just had to use to that we were already increasing. And so, not a great solution, but short of field making other connectors or doing something else, I don't know of another solution. And of course, we're introducing more potential risk here. So, Rob, it's a great question, and I don't know if James or David, if you have a better answer than that, but that's really
That's
kind of what we're up against.
that's what we push people towards as well. Like even if you get that compatibility paper, right? We don't, there's at the end of the day, it's still not worth the risk.
Sure.
Depends how old the system is.
Yeah, this is true. That's true as well.
Are
Yeah,
the panels still under warranty? I mean, with proper process and systems in place and knowledge and size of the system, you could cut the connectors at the module and make them up there. We know we work with companies that do that, and are so, but that requires a good QA/QC and process and test it. But yeah, the simplest solution and quick one is introduce more failure points. You know, I'm pro reduce as many connectors you can in the system. I'm old school. We used to bring our home runs into our combiner boxes and strip the wires back and land them directly onto the fuse.
yeah.
So if we can remove connectors as much as possible from systems, which is what UL 3741 does, um, that's fantastic. And that's all from a troubleshooting standpoint, from a risk standpoint, production and safety and troubleshooting. It decreases your risk immensely. But back to the O&M practices, I just want to touch point on like when you were talking about MLPEs, there's different methods you have to approach to maintaining the MLPEs versus panel level inverter. You have that monitoring already built into it. So leverage your monitoring, your DAS equipment, or your SCADA or HMI, whatever portfolio you have, but also make sure you validate that by sending a team in the field that inverter on that module matches your plans, your data. And same thing with your optimizers. They have the same capabilities. And then with RSDs, probably start thinking about having, which most of the industry kind of has adopted already, thermography. Really, that really has been, we have, a portfolio of assets that we maintain that have RSDs with string inverters. And that's been helpful as far as indicating, hey, this is how many. So when we go do a PM, we're bringing a box of RSDs with us. In addition to that, we can, we're starting to implement predictability through, the Amasis tool through series resistance testing on RSDs. So
Yep.
just throw that out there.
Perfect. Well, we're right at the top of the hour. I want to make sure we get our info up there for people. 3741 has been mentioned a lot. I just kind of want to do just a quick plug for Mayfield, and we have a lot of trainings on our website. We have a lot of content. 3741 is actually a topic we just covered on this AMA recently, so you can find that on our YouTube channel as well. But take a look at our website as well for a lot of the trainings that we do. Next month, we're going to be talking about power system studies for the C&I, PV, and energy storage market. So something that we're seeing a lot more requirements for and getting that. So I encourage people to sign up for that one. And then I wanted to make sure that we get this our contact info up. We're right at the top of the hour, and I know that there's questions that we weren't able to get to all of them. I really appreciate people joining in and putting in the questions. I got a couple. We'll reach back out or make sure that we get answered for you. But yeah, if there's specific questions, you can reach out to us at Mayfield specifically, and then James and David have their contact info here as well. So. Thank you so much, guys. I really appreciate your time. I appreciate you in the audience. This has been a great discussion. And as always, it's such a joy to have you guys and be talking with you.
Thanks. Appreciate it.
Thanks, Ryan. Thanks, everybody.
Thank you, Mr. Nagel.
Thanks all. Have a great day.
Bye.